Our next speaker is Damianos Christos from Radboud University, and he will talk about detection and analysis of DNS tunneling techniques. And this is a pre-recorded presentation.
Hello, my name is Damianos Christos Nikou, and I would like to present you my master thesis research about the detection, analysis, and measurement of DNS tunneling techniques. The research realized by SIDN Labs, and I would like to tell thank you to my supervisor Moritz Miller. Uh, my research purpose is based on .NL ccTLD level that I try to detect, analyze, validate, and measure of the DNS traffic about the DNS tunneling queries. The implementation of this research based on SIDN's authoritative name servers and by using ENTRADA tool. The DNS tunneling includes the following features. This technique is utilized embedded data into DNS queries and responses and create a covert communication between server and client. In addition, bypass network protection such as firewalls and etc. and hidden into legitimate DNS traffic. Finally, modified authoritative name servers to process exfiltrated data and transmit data in restricted environments. Now, the DNS tunneling tools split it in two parts as a server and client side. The client side installed on user machine acts as a stub resolver and serves the server on DNS hierarchy. The server side resides on command and control server and masquerade as authoritative name server. Here, the DNS tunneling tools also have two types of DNS tunnels, over UDP and over TCP. The detection of DNS tunneling include two different methods. The first method, two different methods. The first method is payload analysis that include the size of the request, the entropy of the subdomains and uncommon record types, and the traffic analysis that include the volume of the DNS traffic per IP address, the number of host names per domain, the volume of NX domain responses. As you can see here, we have some examples of these rules that included on these methods, and we have here the implementation environments are the DNS testbed and ENTRADA tool. Now here I have a little bit explanation about the DNS testbed environment that we can see in here that we use the real minority of .nl traffic with root.nl and my own web name server, and we use an extra machine that includes the iodine server, and here is the attacker in our case, and that give commands to iodine client that is in the side of a recursive resolver. Now, the ENTRADA tool environment is an open source tool that retain the DNS traffic of .nl and retain the DNS data more than a year. Also, keep the DNS queries in human readable format, and these DNS queries capture as a pickup files and select a specific dataset of .nl traffic. In data processing, we can use custom rules on SQL queries to extract specific DNS queries, drop queries that unlikely caused by DNS tunneling and select potential DNS tunneling queries. Additionally, we apply custom detection rules on the extracted DNS queries and use scripts for analysis of DNS packets. Here in this slide we present the custom detection rules that implemented in .nl traffic. Rule 1 detects the entropy of the query names per label. Rule 2 detects the encoding per label. The encodings is here like base 32, base 64, hex, and netBIOS. Rule 4 detect the continuous sequences of characters and numbers. Rule 5 detects the characters Y and Z in the first and leftmost label of a DNS query, and Rule 6 detects the NX domain responses that we make a new DNS resolver which requests the queries to check if exist or not. Here I have an example of two queries based on the custom detection rules. The rules 1, 2, 3, and 6 is based on literature analysis, and the rules 4 and 5 is based on observation on DNS testbed. In general, all these rules based on observation of DNS testbed and literature analysis. Now, for the validation process of DNS tunneling, create a scoring system based on detection rules. The weights of the scoring the system based on the importance of the rules on literature analysis and DNS testbed. The score on DNS queries assign the likelihood of DNS tunneling. And now, on the other hand, we have a real user validation that we ask him to utilize the attack on .nl traffic. And after this utilization, we implemented the custom detection rules to a specific day that we detect the first DNS tunneling query. The query observed similarly on DNS testbed in the beginning of the iodine DNS tunneling tool. When we detected this query, we asked the user to verify his IP based on our findings, to validate our findings. Here we have an example of the validated DNS tunneling query that detected in .nl traffic. You can see here the null resource record, the Y in the leftmost label, the continuous patterns, and the NX domain response that we received as the first DNS tunneling query, similar to our observations. So, also in my research, we have limitations, two limitations. The first limitation is the QName minimization, and the second is that we use the only DNS queries. The QName minimization disabled in my research because we want the full version of DNS queries and not split it, as you can see here in our figure. The second limitation is that we use only DNS queries and not responses, and because is the basic operation of the .nl ccTLD level. We have only queries, we don't have responses, and for this reason it was hard to validate our results about the DNS tunneling detection. So, the measurements of the DNS tunneling on .NL traffic implemented over several months, over a specific date, and over a single domain name. And the attributes of these measurements included the frequency by origin country, the resource records of DNS queries, the unique IP addresses, and the number of DNS queries. Here we have an example of several months on .NL traffic. These measurements are separated in between total and filtered data. That means that we measure the raw DNS data of these days and in filtered data after the usage of the custom detection rules. And here you can observe that the US and as a raw data and also as filtered data keep the highest ratio of in both cases. And here you can observe as a top 6 ratio as in potential DNS tunneling queries in the filtered data, you can observe the Russia. Russia included in our potential DNS tunneling queries. So, here our conclusion about this research. The DNS tunneling is being used in the wild and can be detected in ccTLD traffic. The DNS tunneling query features like high entropy, encoded types, uncommon resource record, and NX responses. Also, we observe the highest ratio from US in .NL traffic, and Russia included on the top 6 ratio in potential DNS tunneling queries in .NL traffic. And another interesting observation that we have, you can see more about it in my research paper. We detect that after the implementation of the custom detection rules, we observe almost 3,000 unique domains remain in a specific day, remain as a potential DNS tunneling domains in this day. Also, the custom detection rules can apply in all levels of DNS hierarchy and are universal rules that you can use it in to each ccTLD. Also, the DNS tunneling is common used in daily traffic of .NL traffic. So, something about the future work, we can do future work by using DNS tunneling with QName minimization. We can continue also to do more in-depth analysis of identified queries with custom rules on ccTLDs and on root DNS servers, and we can use machine learning detection of DNS tunneling to detect by machine learning the DNS tunneling by using models and train data on this case. So here you can see my LinkedIn profile that you can visit me and ask me about my research, and here also I include from SIDN Labs website my master thesis that published before some months, and thank you for your attention. Questions?